In this video, we're picking up with assignment 19.0, and we're going to learn how to graph the inverse functions of sine, cosine, and tangent. So we have two different symbols. The inverse of sine that you've seen on your calculator is the F inverse symbol that looks like an exponent, but it is not an exponent. You read this inverse of F inverse of x equals inverse sine. So when we put this -1 on a function rather than on a variable, it's not an exponent. We say the word inverse. F inverse of x is equal to inverse sine of x. And then historically, long before that became popular with computers and calculators, the more historical symbol for the inverse of sine is arc sine. And we'll use those interchangeably. All right, so what does the graph of inverse sine or arc sine look like? Well, we learned in our review of inverses that to have an inverse or to be invertible, a function has to be 1 to 1. So if I graph a sine wave, you can see that it is really going to fail the horizontal line test. Yes, it's a function, so it passes the vertical line test, but not the horizontal line test. So this is at pi over 2 and pi, 3/2 pi, and 2 pi, so hopefully this comes back to you. So we can't do a graph of an inverse because you can see that here these two y-coordinates are repeated. So it's not invertible unless we restrict it to just one piece of its domain. So now what we're going to do is look at that sine wave and make sure we don't go through any hills or valleys. So that's the way I always remember this, is we want to stop from a minimum to a maximum. If we went any farther than that, then it would fail the horizontal line test. So this endpoint is at pi over 2, 1. This endpoint is at negative pi over 2, -1. And of course it goes through the point 0, 0. So I'm going to restrict the domain from negative pi over 2 to positive pi over 2, just like we could only keep half of a parabola in our last video. So now I'm going to erase some of this sine wave that we're not going to use here. And now we're ready to graph the inverse. So again, thinking back to our review, inverse functions fold across this diagonal line, y equals x. So our inverse graph is going to have each of these coordinates reversed. So it's going to have the point 1, pi over 2. So pi over 2, remember, is about 1.5. So it is bigger than your amplitude of 1. So these 2 points are meant to fold across the 45-degree line. So our inverse function is going to flip-flop, and this endpoint is going to fold across. I'm not doing this perfectly, but I mean for that to be the reflection image. So if you trade your x's and your y's, so remember that pi over 2 is a little bit more than 1.5. So this green graph is what the graph of inverse sine looks like. And with a little practice, you'll remember that just as easily as you remember what a sine wave looks like. All right, let's try the same thing for arc cosine or inverse cosine. So let me first remind you of what our cosine wave looked like. Remember that at 1, our cosine started, or at 0, our cosine started at its maximum value of 1. So it went backwards this way. So we had the point pi over 2, pi, 3/2 pi, and pi. So again, we can see the problem with our cosine wave here is that it fails the horizontal line test. So we have to restrict the domain. Now notice we can't go from negative pi over 2 to pi over 2 this time, because that would fail this horizontal line. So So we need to do a different restriction here. So the restriction, and again, my suggestion was to think about keeping only a section that goes from a minimum to a maximum or vice versa, and stay close to the origin. So here, from a hill to a valley, we could do our restriction of our domain from 0 over to pi. So you'll have to remember that inverse cosine has a different restriction than inverse sine. And now we're going to fold it across the line y equals x. And I regret that I didn't. I drew my graph a little too high. And I'll tell you why I'm thinking that, because this point is at pi negative 1. This point is at 0, 1. And I need to flip-flop those points. This point right here was at pi over 2, 0. So now what I need to do is their inverse functions. So where is this going to reflect to? It's going to fold across over to negative 1, pi. So I have to have a point way up here. This point is going to fold across the reflection line. So let me move that even a little bit higher. So this point, if I can get a stylus, is at negative pi, negative 1, pi, writing it backwards. And this point that was at pi over 2, 0 is now going to be at 0, pi over 2. So it is going to fold across the reflection line. And this point that was at 0, 1 is now going to be here at 1, 0. So our reflection image, the blue graph, is going to be what we have to learn is the graph of inverse cosine or arc cosine. So y equals, or f inverse, I was using g, inverse of x equals inverse cosine of x. Or you could say arc cosine of x. So we'll have several days of practice to get used to the restrictions and how to flip-flop those x's and y's. All right, our graph of tangent. So this is a good review. Our tangent is the y over the x in the unit circle. So remember that at this point, 0, 1, y over x is undefined. And this point is at 0, negative 1. So when we do y over x, it is undefined. So the division by 0 was where tangent had its vertical asymptotes. So we're getting more familiar with division by 0, giving us vertical asymptotes in rational functions and in trig functions. So these were our vertical asymptotes. And in quadrant 1, our tangent was getting large. And in quadrant 4, backwards to negative pi over 2, our tangents were negative. So this is what one branch of our tangent curve look like. So this is y equals tangent x. Here I called it h of x equals tangent x. And now we want to fold it again across the 45-degree line for its inverse. So I think I need this to be a little, let me do some erasing here before we get too far. Let's make our, let's make our tangent curve a little more reasonable there, and our reflection line. And think what happens when you fold this across the 45-degree line. The horizontal asymptotes are going to turn into vertical asymptotes. So we're going to have an asymptote now as a horizontal at pi over 2, and a vertical and a horizontal asymptote. The other vertical asymptotes folds down here. And our red graph is going to fold across and look like this graph. So once you get used to the idea of the reflection, then this is our graph of arc tangent, or here we could call it F, no, H. I should make those both be the same. H inverse of x equals tangent with an inverse symbol. So these two are interchangeable symbols. So notice that our restrictions here were the same as they were for arc sine. So from negative pi over 2 to positive pi over 2. So that's what I did this little summary here for, because it's going to take a few days for you to get used to this. And it's something that I know from teaching calculus that the guys will forget, that the restriction on inverse cosine or arc cosine was different than it is for sine and tangent. So we will practice that repeatedly. All right, how will you, in addition to graphs, how will you use inverses? Remember that whenever we do an inverse, this is like giving you the y-coordinate, and you have to find the x-coordinate. So if I ask you for the inverse sign, this is the answer, and you have to find the angle that has that sign value. And I think you notice that that's the long leg of a 30, 60, 90. So what angle has an inverse sign? Square root of 3 over 2, that would either be 60 degrees, or I hope you would think radians, pi over 3. So when you get an inverse cosine, you're thinking this is the answer. What angle has a cosine of negative 1/2? And I hope you're thinking of this angle, because arc cosine was restricted from 0 to pi, so that would be at 2/3 pi, or 120 degrees. And arc tangent of 1, where is the tangent equal to 1? That's the ratio of vertical to horizontal, and that of course was in a 45-45, or pi over 4 radians. All right, so when you are asked to do inverse sine of negative 1/2, you're thinking backwards. What angle has a sine of negative 1/2? So why would it be wrong to say 11/6 pi? Isn't it true that we're at this triangle, that this triangle has a sine of negative 1/2? It is true, and it looks like that angle could be called 11/6 pi. But remember our graph? Remember our graph of inverse sine only went from negative pi over 2 to positive pi over 2. So it's just a matter of renaming it. So instead of calling it 11/6 pi, we're going to rotate backwards. So we have to call this negative pi over 6 to stay within the restriction of negative pi over 2 to positive pi over 2. All right, and then what if you were asked to do the inverse cosine of a cosine? Well, mathematically, I hope you would say, well, doesn't doing an inverse undo a cosine? But the problem here is this negative pi over 6. Remember that arc cosine had a restriction from 0 to pi. And it will take a while to get used to this, but start working on memorizing. So negative pi over 6 is outside the restricted area. So if you did negative pi over 6, you would be down here. So we would like to say that the cosine of negative pi over 6 is square root of 3 over 2. And then we want to, let me erase and try that again. I think you're not going to be following me. Let me show you with perhaps a highlighter here. I'm going to do this part first. So the cosine of negative pi over 6 right here would give us a square root of 3 over 2. And then we want to do the inverse cosine. So now what angle has a cosine of square root of 3 over 2? We don't want that same angle because it's outside of our restriction. So we have to stay between 0 and pi over 2. So we want to say this triangle has the same value. So we don't want negative pi over 6. We want to answer pi over 6. So we have to stay for an inverse cosine. We have to stay within 0 to pi. So that's our correct answer. And we'll repeat and review that again in the future assignments.